Take a flexible, closed loop and try to pull it off a one-dimensional ring. It remains completely trapped. But take that exact same loop and place it on the surface of a three-dimensional sphere, and it slides off without resistance. Understanding why these shapes behave differently is a core objective of algebraic topology. In this field, we classify spaces by finding invariants, properties that remain constant no matter how a shape is stretched, bent, or deformed. We will use a tool called the fundamental group, denoted as pi1. It detects one-dimensional holes in a space by observing how closed loops behave when you attempt to shrink them to a point. To demonstrate this, we'll work through the mathematical derivation in section 59 of Munkres Topology to analyze spheres, then move to section 60 to build and calculate the group of a more complex surface. Because we are working with formal proofs, the visuals will remain focused on the whiteboard, minimalist diagrams, and logic on a dark background. Our goal is to move past visual intuition and translate these topological shapes into pure, rigid algebra. We begin with the circle, S1. The fundamental group of a circle is isomorphic to the integers, z. In S1, the behavior of a loop is determined by its winding number, the number of times it wraps around the central hole. However, for any sphere Sn, where the dimension n is 2 or higher, the fundamental group is trivial. It is simply 0. Consider a 2D sphere with a 1D loop. Because a curve can't cover the entire surface, at least one point P lies outside the loop. Removing P allows stereographic projection, unrolling the sphere into a flat 2D plane and carrying the loop with it. This punctured sphere is homeomorphic to flat Euclidean space. Because flat space contains no holes, any loop within it can be shrunk along straight lines until it collapses into a dot. This explains why loops are trapped on a circle, but not a sphere. Higher dimensions provide the spatial degrees of freedom to untangle. Calculating the fundamental group of more complex shapes, like the torus, is difficult if we only look at the three-dimensional model. Topologically, a surface is a space that is locally homeomorphic to R2. Zoomed in, it looks like a flat plane. This property allows mathematicians to construct three-dimensional surfaces using the quotient topology. We start with the fundamental polygon in Munkres figure 22.1. This rectangle is a blueprint. First, we glue the top and bottom A edges, transforming it into a cylinder. Then we glue the circular B edges together, forming the final torus. To perform algebraic calculations on this shape, our quotient map must follow the specific consistency requirements defined in section 22.
By utilizing this blueprint method, we can determine the properties of a three-dimensional surface without needing to visualize the final shape. We can now calculate the fundamental group of the torus using only its two-dimensional polygon. We first identify a base point. Figure 22.5 shows how all four corners of the flat square merge into one single point. This defines our group's generators. Edges A and B become distinct loops intersecting at this new base point, shown in figure 22.6. We find the algebraic relation by walking the perimeter. We travel forward along A, forward along B, backward against A inverse, and backward against B inverse. Because the interior is a solid disk, this entire boundary path shrinks to a single point. Algebraically, this means the path A inverse, B inverse is contractible, so it equals the identity element, 1. Rearranging this equation shows that AB equals BA. This confirms that the two loops commute. Therefore, the fundamental group of the torus is the free abelian group on two generators, V cross C. This shows the power of the quotient method. Changing the arrow directions on the blueprint allows us to identify algebraic signatures of completely different shapes. The fundamental group provides a mathematical signature that allows us to distinguish between spaces that might look similar but possess different structures. When we compare these spaces, the differences are clear. The circle maps to the integers, higher dimensional spheres map to 0, and the torus maps to Z cross C. The distinction between the circle and the sphere depends on the dimension of the environment, which determines if a loop can be untangled. With the torus, we bypassed three-dimensional modeling entirely by reading algebraic structure from a flat blueprint. Topology provides the rigorous framework required to translate continuous geometry into discrete algebraic facts. If you found this derivation helpful, subscribe for more in-depth mathematical proofs from the classics.